Well, once again, we're at the physics video lecture. Welcome. It is Psci 168 video lecture 29. Okay, we're wrapping up the heat engine material, but you're going to see right now it's just going to keep getting better. So we had a pretty technical discussion of the efficiency of the heat engine last time, and I'll go ahead and put the schematic up there and repeat that discussion a bit, and then we'll see where it takes us. What we're going to do is generalize the idea of the heat engine, and I'll have a lot of interesting things for you guys to pursue and get printouts of. Okay, so with the heat engine, now that we've studied it, we've seen a couple of examples, and I'm going to begin with the schematic of the heat engine. So for all of the examples, we can reduce it to this idea. We have the high temperature reservoir. It delivers some thermal energy. So these are Kelvin. This is some number of joules to the engine, whatever that may be, and that thing kicks out some work. Okay. But in order for it to be a cyclic process, there has to be what's called the waste heat, QC, to a low temperature reservoir. That can be the atmosphere, that can be a body of water, which you use to cool off the engine. And so yeah, we have all of these, but no more than these quantities in the whole process here. So when we construct the efficiency, that's just a natural definition, the work divided by the energy you put in, right? You can be burning fuel, you can do a number of things here. Okay, but for the ideal, I'm going to write ideal engine, we have 1 minus QC divided by QH, and this was just energy conservation. Check those notes out again, how we got that. Then we have the Carnot efficiency, which was the grand result here. That efficiency is 1 minus this ratio of operating temperatures. Okay. So E sub C, Carnot efficiency. Carnot efficiency, and I can also express this just by getting a common denominator, TH minus TC divided by TH. In this second form here, let's go ahead and put a box around this whole thing. In this second form, we see really explicitly, if we want to get the highest efficiency, we have to have a large difference in temperatures. Okay. The difference in temperatures has to be large. This middle form here, we see that we want TH to be much larger than TC, and that way we're taking away very little from the 1. The 1 would be the ideal, right? 100%. So in either case, you see we need a difference in temperatures that's very high. And here we see that the higher the high temperature, the better. Okay, so why is this so important? Because this is a principle bound, and we're trying to get as much work as we can out of our energy source. Another thing we can then do is start looking at nature for temperature differences. Are there temperature differences available in nature that we can harness for our heat engines? Okay, so that's why this abstracting is so important. Plus, it's really just a huge triumph for physics to be able to boil it down to such a basic expression here. Remember, this simply depended on entropy increasing. Okay, so as fundamental as anything. Okay, now let me give an example of a heat engine that does not burn fuel. go ahead and write this down. Temperature differences, we also refer to those as gradients. Temperature gradients in nature can be harnessed, okay, can be harnessed. Okay, big star here. So the example I'm going to give is something called the solar chimney. Example, the solar chimney. Now these types of schemes that I'm going to describe, they may not be the solution to all of our problems, but they're an important, all of our energy needs, but they're really important to understand what you're up against and what you're trying to do. Okay. So the solar chimney is the following. You have a canopy, a very large canopy, and I'm going to have you guys look up some pictures of this. So this thing could be as big as a football field, and maybe high enough to drive a car under. Okay, and it's open from the sides and it's transparent. And right in the middle here, there is a large chimney that connects. There's our solar chimney right there, okay? And you guys are going to look up some images of these. These things have been built. So where's the temperature difference here? Okay, what we have is sunlight. Okay, so solar radiation, fancy way of saying sunlight. Let's write it down, sunlight. Heats the air, goes through the transparent or translucent top, heats the air underneath. So what does that mean? It means we have a higher temperature air down here, and the chimney's as high as you can make it. And up here we have lower temperature air. So there may have been a natural difference in temperature between the ground and somewhat up off the ground, but what we've done is we've increased that natural temperature difference. So now we have hotter air underneath, cooler air on top, and that's enough to set up a chimney effect, the convection. So now we have, since the sides are open, air coming in from the side being heated, going out the top. So now we've constructed a chimney that naturally has air blowing through it, and then it's just a matter of building some turbines in here. So they put some little propellers in here, and then if you know how to turn that energy into electricity, you're on your way, okay? So turbines, right, this here is convection. So you see, convection, that's just the wind. So you see we had to study the heat transfer by convection. We got high temperature, low temperature, heat transfer, and air current. So instead of the candles on our Christmas pyramid, we have just this natural temperature difference there. So yeah, for homework, you want to look that up and get some images for your notes. But the idea there is pretty clear. It's right out of our discussion. And what else you can see is good. We have heat transfer. Let me make a little list here. So we have heat transfer by convection. And that's what wind is. Okay. So when we talk about wind energy, that's what we're talking about. And we have up here, of course, we had heat transfer from the sun to our Earth by radiation. So we have the heat transfer by radiation. There's certainly conduction in there as well, but it's not the main conceptual point right here. Okay. So there's a temperature difference. accentuated it by separating. Remember I showed that chimney effect on my Christmas pyramid deliberately, because when you create that chimney, you really can funnel the wind that way and make a true separation between higher and lower temperatures. So what is the efficiency of this machine? So maximum efficiency, that's why we're studying this. So before you even build this thing, you can know what the maximum possibility of, the maximum amount of energy that you're going to be able to get. Okay. So the efficiency, the maximum efficiency, 1 minus Tc over Th, and this is going to be, I'm just going to make up some numbers, example. So I do the Th minus Tc version over Th. And what are we going to have there? We're only going to have a few degrees Celsius between the bottom and the top. Remember, this is not an enclosed greenhouse that really builds up a lot of heat. And even that wouldn't be very hot. But in fact, it's being replenished with cooler air from the sides at all times. So it's just going to be a couple of degrees Celsius divided by, roughly 300, since we're talking about Kelvin, right? So it could be, say, 5 would be a lot divided by 300. And 5 over 300 is not a very big number, okay? It's like 1.5%, okay? So the efficiency is small. And if you're going to build one of these, you have to take into account that the sunlight is free. Okay? You're not putting fuel in it, but the efficiency is small, and it may not be worth it to build some gigantic machine under those circumstances. But yeah, you can calculate all of this. Of course, what we don't know yet is how much energy is contained in the solar radiation. I usually do that a bit later in the semester, but actually we're going to segue into solar energy within an hour or so of this class. Good, so this is our solar chimney. I want you guys to look it up. And here we'll just put this question: how much energy? And we'll get to that soon. That's of course very interesting. You want to know how many, how many joules, how many kilowatt hours are there in solar energy? Okay, so that's one example. Let me consult the clock here. Great. Now my next example is going to be this object here in nature without the chimney. And what would this be if there were no chimney involved, no machine? Actually, it would be a hurricane or a tornado. So hurricanes and tornadoes. Definitely going to send you guys out to get a picture or two of a hurricane and a tornado, because once you understand the solar chimney, then the hurricane example, hurricane is kind of big, but works on this tornado, which is a smaller version. Definitely get some images of hurricanes and tornadoes. So here's what we have going on there. We have, here's the ground. We have warm air. If it's moist air, it's even better. Okay, moist plus moisture. And we have some kind of atmospheric condition that has the winds opposed to each other. So the shear condition for the winds, because that's where that funnel cloud comes about. In fact, they may start the funnel cloud may actually start more horizontal from a shear condition, but if it dips down to the earth, then you're putting in contact a low temperature and a high temperature, I'll put TH down here, regime. Oops. And yeah, we've got that picture up here as well. And these funnels can twist and do what they do, but the point is that they connect a higher and a lower temperature area. The whirlwind itself effectively creates a chimney. Okay. What it does is it creates, because it has a tangential flow, it creates an area that is separated from the outside. If you throw something in a whirlwind like that, it'll be deflected off. So there really is an inside versus an outside in a funnel cloud. And this is, the way I've labeled it, looks like a heat engine, doesn't it? So that's what's actually running it, the temperature difference between the warm air on the ground level and the colder air, which can be way up, right? This can go up, potentially up into the stratosphere, but definitely quite high where the air is colder. And you have the similar thing for the hurricane, which typically starts out over the ocean in warmer waters, and they're moist. And that's the other thing, as the moisture condenses, that's another thing we studied, right? The condensation of moisture releases an enormous amount of heat. And what that is it releases heat, causes the air to rise even more. So hurricane or tornado as a heat engine. A heat engine, I'll put a question mark there for you, but we just answered that. So homework here as well, images, and along the way you may find some interesting discussions and explanations. But yeah, we definitely have that. We're not going to calculate some efficiency, but it's really the same schema that we've had so far. So the solar chimney is, on the one hand, it reminds us of our Christmas pyramid, and on the other hand, there's a relation here to the hurricane or the tornado. My next example is a combination of these two. I don't think they've really been built yet, but there's a Canadian engineer who came up with the idea of the atmospheric vortex engine. So atmospheric, I'll make sure I write that clearly. This is what I want you guys to look up as well. Atmospheric vortex engine. So the idea there is to build an enclosure. So instead of building a very tall chimney, you have a relatively low enclosure, but it is made with tangential, with veins in it that kind of go tangentially. Okay, with tangential openings, so that when the wind comes in here, when the air comes in from down low, so the air comes in here and it's kicked into, or it's directed into a circular motion. Okay. So this enclosure would be kind of low. And the idea would be, instead of building the large chimney, you have the enclosure in which the wind is directed into a circular motion, and if you can get it started, you're trying to get this kind of funnel cloud drawing to naturally extend all the way up to the stratosphere. In other words, you're trying to construct a tornado that stays in one place. Okay. That's pretty exciting, because what if it jumps out? Okay, then it could be dangerous. But the idea of the atmospheric vortex engine is to hold a tornado in one place. So fix the tornado at, or hold a tornado at a fixed location, or create a tornado at a fixed location. And if you could do that, it would be feeding off the warm air down low. It would be funneling it up to the stratosphere where the air is very cold. And then you would mount turbines wherever you could best use them to capture the airflow and spin the turbines. So turbines, I'll just write inside or out. You have to put the turbines somewhere, to harvest that high wind that you've created. So atmospheric vortex engine, absolutely I want you guys to get some good images of this. So look it up. And what you'll see is we have a progression now. We've talked about, we started with the Christmas pyramid and analyzed that and the steam engine as heat engines. Right, we did the analysis of the heat engine to get the Carnot efficiency, at which point we're going to look around in nature and see if we can construct some devices that will help us harvest energy based on the presence of these temperature gradients. And so this kind of reminded us of the Christmas pyramid, and conceptually at least it did, and then we see that the hurricanes and tornadoes are on those lines, and then the atmospheric vortex engine, which as far as I know, a large one has yet to be built. It would be pretty exciting. In fact, I think this engineer had some ideas of utilizing cooling towers at large power plants as as the foundational object there. And maybe we'll live to see it happen someday. Okay. Very interesting idea. Okay, I'm going to consult the clock again. So with these discussion points and these objects here, what I'm going to do, I usually go into electricity and magnetism because we have to get these turbines and turn them into electricity and get it to our civilization. But I think this time it's actually better if we go into wind and solar energy, because we see in all of these cases we're looking at wind. We want to maybe harvest the energy with wind turbines, and we have to learn how much energy is available from the sun. So that's what I'm going to do next. I'm going to start with a bit of a discussion of solar energy and then some wind energy. And the other thing is there are other solar energy ideas that can then come into play. Okay, let's free up some board space here. We'll leave that up there since it's got some of our themes. But yeah, you guys go ahead and get pictures and maybe a little research on these things. Solar chimney, hurricanes and tornadoes, and this atmospheric vortex engine. So once again, get some pens here. Good, we have the word solar up there on the board. So what we're looking for now is how much energy is available from sunlight. So next, solar energy. So we leave something out in the sun, it warms up. We go in the sun, we're warmed. Sunlight can melt things, etc. That's what we're talking about, solar energy. How much is there? Now we've already mentioned the water cycle, so we know the energy we've been talking about has involved solar energy already, but now we're going to make it quantitative. So how much energy in sunlight? Question mark. You guys saw me light the matches from across the distance of the table. So we saw energy, thermal energy, heat being transmitted. So heat transfer by radiation up here. But we can answer that question with an experiment. And this is really just a controlled version of leaving a hose out in the sun in the summer. So you leave a hose with water in it out in the summer, out in the sunlight, and you turn the water on and really hot water comes out. Okay, that's our experience. So the experiment is going to be a version of that. We have to construct some kind of a box that faces the sun. So I have a surface area. I'm just going to write area A. And this box here contains water. So it has water inside. Water inside mass M. Okay. And we have a thermometer. So there's our thermometer. Some colors here. So there's our thermometer, and we always just do this. Degrees Celsius. So we have a thermometer, I'll write it. And what do we have? Sunlight. Sunlight. So that's our experimental contraption. We are putting this water in, you know, practically speaking, maybe this would be a glass top, and the water would have a bunch of dye in it to dye it completely black, and it would absorb the most rays of the sun, right? Those would be the details. We'd have to do that. But if we put that water in, and then maybe we'd have to stir it up a little, those kind of details as well. But what we would have is, in time, the temperature would rise, okay? The temperature goes up, and we'd carefully make a graph of the increasing temperature. That's our experiment. I'll make some of those points here. So we've got the water in the sun. 1, 2, measure the temperature. T at different times. Times T. And so you make those measurements and then you graph them. So this is the temperature as a function of time. So, other way around. Other way around. So the temperature as a function of time. Temperature as a function of time. So T as a function of lowercase t. And you know, it starts out at room temperature, and then it goes up for a while, and eventually it's going to saturate. It probably won't start boiling, it's going to get hot though. So it's going to reach the maximum. Those are your data points, so you've got a graph like that. And what can we say about this? Well, with everything we've learned, we have the following. We have energy is equal to mass, specific heat of water, change in temperature, okay? So that's energy. I'm going to build this expression up. And then the next thing we can do is have power equals, let's go ahead and call this delta Q. Power is energy over time. That's the power, and that's mc delta temperature over delta time. Okay. And then we can have a third quantity, and we're going to call this intensity. Go ahead and intensity. And the intensity is the power divided by the area. Power per area. So we have mc over area delta T over delta T. Okay, with some patience we could do this in the backyard. Now, this delta T temperature over delta T time is just the slope of our graph here. Okay, that's the initial slope of our graph. The mass is the mass of water. We poured it in, so we know that. We know it's the specific heat of water, and the area is the area of our contraption. So in other words, using these ideas, we can calculate or measure the intensity of sunlight. So I'm going to finish with that. Roughly speaking, you do this carefully at noon, and you'll get approximately up to 1,000 watts per square meter. Above Earth's atmosphere, if you're really getting what the sun delivers without any reflection of clouds and air and anything else like that, you get what's called the solar constant, which is a bit more. And so we'll use that as the idealized true, and actually is the true value. And that's my definition of the solar constant. I'm going to end the hour with that. It's a good place to leave us for now. So for this experiment, and similar ones, and actually there are other ways to do this. That's what's nice in physics. You know, there are many different ways to arrive at this number, but this one is good for us because we've studied everything on this graph here, picture, and similar ones. Results in the determination of what's called the solar constant. So the determination of the solar constant. And the solar constant that I'm going to cite is what you would get above the atmosphere. Okay, you're just getting all of the sunlight. And that is I equals 1,340 watts per square meter. Okay. And for rough purposes down here at the surface of Earth, we can just use a nicely rounded 1,000. For example, if you want to calculate what your solar panels will deliver to you, you'll start with this 1,000 watts per square meter, and then you'll have to talk efficiencies. Okay, so 1,000 watts per meter squared on Earth. So that's what the solar constant is. And once you know this, and you just learned it by carefully heating up some water in the sun, you can start to plan how much energy could be available. For example, this contraption here, once you know this number, and let's take the 1,000, so you take this 1,000 for every square meter in the canopy, and then you multiply by that very small efficiency, and that'll give you the maximum possible output of such a device. Good, we're going to leave it there now. We'll begin the next hour with some more discussion of the solar constant. Very important concept. And then we can discuss different ways of harvesting solar energy. This actually was one of them. There will be more. Good, see you guys next time.